Hello and welcome to lecture 28 of the course Theory of Computation. It's also the first lecture of week 6. In week 5, we completed context-free languages, and then we started talking about Turing machines. Right? So we defined what is Turing machine, and we explained when does a Turing machine accept a certain string. Right? So let me just repeat. So Turing machine there is a state control, and there is a tape which is an infinite tape, and which is initially filled with the input. And the main differences of a Turing machine is that differences from a DFA, NFA, or a PDA is that there are special accept and reject states. Right? There's one accept, one reject state. And so once you reach the accept or reject state, you immediately accept or reject. Then the input tape is a read-write tape. It's an infinite tape, right? And these are the main differences between the Turing machines and the previous automata that we saw, right? So we say that a Turing machine accepts a string if there is a sequence of configurations C1, C2 up to Ck, such that C1 is a start configuration. So start configuration means you have the start state being Q0, followed by the input W, right? So W itself is a string. So this means that the input, it will be something like this. So you have Q0, W1, W2, etc., Wn. What this means, this is the configuration. What this means is that in the input tape you have W1, W2, etc., Wn, and the head is pointing to the first location, and the state is Q0. Right? This is the start configuration. And then every successive, like C2 is a valid successor of C1, C3 is a valid successor of C2, and so on. And finally, Ck must be a valid successor of Ck minus 1, and Ck must be an accepting configuration, meaning the state corresponding to Ck must be the accept state. So basically, this is the situation when a Turing machine accepts a string. So recall that when you are given a string, a Turing machine can, there are three possible eventualities. One is that the machine accepts the string. Another one is it rejects the string. So rejection will happen exactly the same way, right? So this is another place where Turing machine differs from DFA, NFA and all, is that rejection. So in DFA, NFA, PDA, rejection was just defined as not accepting. Here there are two possible ways of string not getting accepted. One is that exactly the same kind of thing can happen, but instead of Ck being an accepting configuration, it could be a rejecting configuration, meaning the state in the Ck could be Q reject, right? So TM can reject. So the other possibilities are, two possibilities: TM rejects W, or Turing machine loops on W. So loops, by loops on W, I mean something where the Turing machine is not able to accept, it is not able to reject, it just continues computation forever. So just like if you write a computer program, and if there is an infinite loop, it will never end, but it will also never give an output, right? It never accept, it will never make a decision. This is a similar situation is what I mean by the Turing machine loops on W. So given a string to a Turing machine, there are three possibilities, right, of what can happen. One is that the string gets accepted, two, string gets rejected, three is that the string just continues computation. It neither gets accepted nor gets rejected, right? So that is something that we need to understand, and this is an important difference of how Turing machines are different from DFAs or NFAs, right? So the next definition, the next set of definitions this plays a role. The fact that there are two ways in which a string cannot get accepted, right? So first of all, we define the language that is recognized by a Turing machine. Okay, so notice the word recognized. So Turing machine M is denoted by LM, just like we did for DFA, NFA, etc. it is a set of all strings that are accepted by the Turing machine. Okay, so this is exactly similar like how we did for NFA, PDA and so on, right. L of m is the set of all strings that are accepted by the machine. Okay, so which means there are three, again I want to say there are three possibilities. So there are all the set of all strings in sigma star, some strings are accepted and that is called LM. The remaining strings may not be all rejected. There could be strings that are rejected, and there could be some strings that are neither accepted nor rejected, where the machine just loops on them, right. So LM is a set of accepted strings, and what is important is or what is different here from PDAs or NFAs or DFAs is that the remaining strings that are not accepted, right, sigma star minus LM, right, the remaining strings, there are two possibilities. It could be rejected or it could be looped, right. Anyway, the language recognizable Turing machine is denoted LM, and we say that a language is Turing recognizable, or the other terminology used is recursively enumerable if there is some Turing machine that recognizes it. So just like regular languages where the set of languages that are recognized by some DFAs, or context free languages are those languages that are recognized by some PDA. Similarly, Turing recognizable languages are those languages that are recognized by some Turing machine. Okay, so which means L is Turing recognizable if there is some Turing machine M such that L is the language recognized by M. And another word for Turing recognizable, so I will maybe use it, is recursively enumerable. Okay, so this is another terminology for Turing recognizable. So in CIPSR they predominantly use Turing recognizable, but if you look at some other books like Hopcroft and so on, they use the word recursively enumerable. So I will be following CIPSR, so I will be mostly referring to it as Turing recognizable, but I'm making this this remark so that in case in the future, keep this in mind. So in case you are referring to some resource which uses the other definition, you should, or the other terminology, you should be able to you should be familiar with it. Okay, so L is Turing recognizable, or L is recursively enumerable if some Turing machine recognizes it. And this is something that I already said. Given a string, there are three outcomes possible: accept, reject or loop, right. So now based on this, there is another definition. So we say that a Turing machine M decides L. Okay, or in other words, we say that M is a decider for the language, the Turing machine is a decider for the language, if the language recognized by the Turing machine is L. So LM is equal to L means the language recognized by the Turing machine is L, meaning the set of all strings accepted by the Turing machine is L. This is same as M is the language recognized by M is L, and the second condition is that M always halts, meaning looping is not an option. This means that M decides L if there is a Turing machine, M decides L if M accepts all the strings in L and M rejects all the strings not in L, right. So if you want M to recognize L, if you want M to merely recognize L, you just want the strings in L to be accepted and the strings not in L to be not accepted. So not accepted could be in two possibilities: reject or loop. However, when you are talking about a decider, you want all the strings in L to be accepted and all the strings not in L to be rejected, meaning you are not allowed to loop on any input. So M always halts means strings not in L are rejected. No looping is allowed. So decides mean you are not supposed to loop on any input. This is what you say. This is when you so notice that we say M recognizes L and we say M decides L. So deciding is actually, so when M decides L, M is also a recognizer for L, but decider, if it has to be decider, there is more constraints on it. So a decider is also a recognizer, but a recognizer need not be a decider, because there could be strings that are not in L on which M is looping. Okay. So we say that L is decidable, the language is decidable if there is some Turing machine M that decides it. Okay. And just like I said, recursively enumerable, another terminology for decidable is recursive. So we say that so some nodes may refer to it as recursive. So L is decidable if some Turing machine decides it. Okay. So once again, three possibilities exist: accept, reject, and loop. If a Turing machine, the set of strings accepted by a Turing machine is L, we say that the Turing machine recognizes L. Further, if no string is rejected by the Turing machine, we say that the Turing machine decides that language, right? So I'm sorry, if L is a language recognized by the Turing machine, we say the Turing machine recognizes L. Further, if no string loops on the Turing machine, meaning all the strings that are not in L are rejected, we say that the Turing machine decides L. So we want the Turing machine to halt on all the inputs. No looping is allowed. Okay. So this is the difference between recognizing and deciding. A Turing machine that decides a language also recognizes that language, but then a Turing machine that recognizes a language need not be a decider, because there could be some strings that loop on it. So intuitively, since some of you may be familiar with the course algorithms, a decider is like an algorithm. So when you run an algorithm, you always want an answer, right? So you want to know something graph is connected or something is 3-colorable. You want a yes no answer. So the answer could be right. You want a yes no answer, right? So you don't want to give an input and just not hear back from the algorithm. So decider can be intuitively thought of as an algorithm. Okay. So these are the main definitions, L being Turing recognizable and L being decidable. So now let's see some examples of Turing machines, okay, or some like examples in the way Turing machines can operate. So the first example is a language. It's a unary language. 0 power 2 power n. Okay, so 0 power 2 power n means it's a string of 2 power n zeros. So it's a unary language. So that is so it's entirely zeros, but the number of zeros in the string is going to be a power of 2. Okay, so the strings in the language are something like 0 is in the language, 0 0 is in the language, 0 0 0 0 is in the language, right? But so all these are in the language, but let's say 0 0 0 0 0 0, this is not in the language, because 6 zeros is not a power of 2, right? So how can a Turing machine be programmed to decide this language? Okay, so we will talk about how the Turing machine operates at a high level, and then we'll get into the details, or we'll not get into the entire details, but we'll just say that everything that we say here can be implemented in detail. Okay, so what we do is, let's say I'll just draw so tape here, something like 0 0 0 0 0 0 0 0, and that's it. Okay, this is my tape. So there are 8 zeros. This is in the language, right? 8 is a power of 2. So what we do is move from left to right and crossing off every other 0. Okay, so meaning you start with 0, the next 0 is crossed off, next 0, then the next 0 is crossed off, next 0 is crossed off, next 0 is crossed off, right? So now you come to the blank. So now you see that you are at the rightmost end of the string, right? Now what you do is, once you are at the end, you return to the left side. And if at this stage, if there was an odd number of zeros, meaning if instead of the space here we had a 9th zero, right? then we would have rejected, right? So 9, because 9 is not a power of 2. But anyway, now we have a space here, and we will continue. So now we come back to the left. Okay, so now you start with the first 0, then 1 is the crossed off 1, we can just skip over. So the next 0 you cross off, then the 0 which is originally in the 5th position, then the 7th 0 is crossed off. Okay, then you see that you are again coming to the end, then you come back to the left side. So now you have only 2 zeros, the first one you see and the second one you cross off, and again you come back, and now you see that there is only 1 0, right? So because it's only 1 0, you accept, because that's the conditions said. If there is only 1 0, you accept, and if at any point you see a number of zeros is an odd number greater than 1, you reject. So in this case we didn't encounter that, because 8 was a power of 2, so 8 became 4, 4 became 2, 2 became 1. However, if we had started off with some other number, let's say we had started off with 6 zeros, 0 0 0 0 0 0, right, what would have happened is, first you cross off this, you cross off this, and you cross off this, then you come back to the left side, then you see the first 0, then the next 0 is crossed off, then you see the 0 in the fifth spot, and then there is no other 0 to cross off. Right. So now we had 3 zeros that were remaining. 3 is an odd number greater than 1. So which means at this point it is rejected. So this is what you do. This is how you can check whether the number of zeros is a power of 2. Right. And the algorithm is written in a bit of detail over here, but this is still high level, right? Because I am saying things like move the tape from left to right. But the definition of a Turing machine, if you remember, it involved states, and each the tape head reading something, and then each move going to left or right, right? So now I am talking about moving from left to right entirely. So how will that be programmed? So the point I want to say is that all that can be done. So most of what we say here, all of this can be accomplished using states and appropriate rules. So just to illustrate, but then if we go into that kind of detail, we will end up spending too much time and too much effort. So what I would rather do is to explain one small task how that is done using such rules. Okay, instead of explaining everything to the detail, I'll just take up one small task and explain how that can be accomplished using the Turing machine rules. And now you will just have to take it from me that any of these rules, like if the number of if only 1 0 you accept, number of zeros an odd number you reject, all these kind of rules can be accomplished. Return head to the leftmost position, all of this can be accomplished. So what I want to just explain in full detail is, given a string like this 0 0 0 1 1 0 1, how can we, using Turing machine rules, put a hash symbol to the left side and then shift everything to the one step to the right. Right. So this is what I am talking about. So you given a string, given a binary string, I want to shift everything to one side, one step to the right, and put a hash symbol in the left side. So this is what I want to do. So this is a Turing machine that will just do this operation. It will not really like check something, right? So here it was checking whether the number of zeros is a power of 2 or not. But here there is no checking, because it is just asked to execute something or do some operations, right? So it will just do the operation and accept. There will be no reject, because there is no scope for rejection. Okay. So now we have the Turing machine. It has two symbols, two input symbols, 0 0 0 1 1 0 1, and the tape symbol, there is a hash. Okay, and at the end of the operations, the tape will be the tape will have the required thing, meaning the original input shifted by one step to the right and the hash symbol. And there are 4 states, or maybe more than 4 states. There is a start state QS. There is a state 0. Okay, there is a Q0, there is a state Q1, there is a state Q2, and there is an accept state. Okay. So start state is Qs. So note the small difference. Instead of Q0, I am calling it Qs. Right. Okay. Start state is Qs. So 1, 2, 3, 4, 5 states. Qs, Q0, Q1, Q2, and Qa. So let us see what these states do. Right. So originally, so maybe we'll see this through an example. Let us try to work out some example. Let's take a different color. Maybe let's say 0, 0, 1, 0, 1, 1, right. So this is the string, and this is blank, blank, and so on. So this is the string that we want to, and originally we are here, okay, and we are in the start state Qs, okay. So let's see what happens. So initially is Qs and 0, right. So we will use this rule. Qs0 is Q0 hash r, okay, Q0 hash r. Meaning what do we do? So we move to state Q0, okay, so we move to state Q0. So I am just writing the states below, and the 0 is replaced by hash. So the 0 is replaced by, maybe I will use a different color, 0 is replaced by hash, and one step to the right. Okay. So basically what this Q0 indicates, right, so this 0 in the Q0 indicates is that the last symbol that it saw was a 0, right. So that's why we have Q0 and Q1. So we'll come to Q2 later. Q0 means that, so now I have erased a symbol 0 and put a hash, and I need to remember that it was 0 that I erased, and that is what we are accomplishing through Q0. If it was a 1 that was erased, we would have gone to Q1, right. Qs, if the first symbol was 1, we would have gone to Q1, right. See, this is Q1. Anyway, now we are at Q0 and at the second symbol. So because we erased a 0, we are at Q0, and because we are at Q0, now we will write 0 also. So let's see what. So now we are at Q0 and we are reading 0. So we have to follow this rule. Q0, 0 is, you are again going to Q0. Okay, so you are again going to Q0. But you write 0 also. So thankfully it's already 0 there. So you write 0 and then you move one step to the right. So you're again at Q0 and you move one step to the right. Because it was 0 earlier, I'm not going to erase and write 0 again. Okay. So now you are at Q0 and reading a 1. So the rule to be used is this one, Q0, 1. So now you have to go to state Q1 and write 0. And move one step right. So you go to state Q1, okay, and write 0, and move one step to the right. Okay, so now you are in state Q1. Now at Q1 you are seeing a 0. So you have to use this rule. Now you have to write 1 and you have to again move to Q0. So you have to write 1, okay, you have to write 1 and again move to Q0. So let us see. You have to write 1 and again move to Q0, which I have written here, and then move one step to the right. Okay. So now you are at Q0 and reading a 1. So which means this is the rule to be followed, which means you will move to Q1. Maybe I'll write here, you will move to Q1 and write 0, write 0, and then move one step to the right. So because you are at Q1, now you are at Q1 and looking at 1. So now this rule has to be imposed, which means you will remain at Q1, okay, so you will remain at Q1, but you will write 1, which is already 1 anyway there, and then you will move one step to the right. Okay, so now you can see how using these states I am keeping track of what I just erased. Right. So now we come to blank, but you are at Q1. So what is the rule to be applied? It is this one. You are at Q1 and then reading a blank. So Q1 means the last symbol you erased is a 1. So which means this blank should be erased and 1 should be written here. Okay. and because we just erased a blank, we know it was the last spot. So and then we move to Q2. Okay, so Q2 means that now we have come to the rightmost endpoint. This is the meaning of Q2, which means now it is a signal for us to move to the left, because at the end I want to come back to the left side and stop. I could have stopped here, but just for completeness I want to come to the left side and stop. So now let us see what Q2 does. The rules for Q2 are, if it sees a 0, it writes a 0 and moves left. If it sees a 1, it writes a 1 and then moves left, meaning it leaves the symbol unchanged, right. So now what will happen is that it is at Q2 and at the last position. It will come to one step before and leaving the 1, and again it is here, so it will come here leaving the 1, it will come here. It will always be in Q2. So Q2 it will go one step to the left, one step to the left, and so on, and finally it reaches the hash symbol, right. So when it reaches the hash symbol, we know we put the hash symbol at the leftmost point. So when we reach the hash symbol, we know that we have reached the leftmost point. So then this rule applies. So Q2, at state Q2, reading the hash symbol means now you are done with whatever you set out to do, which means you can move to QA, which is the accept state. So then you complete the execution. So once you come back to the leftmost point, you accept and you are done. So there is a left move that is said here, but this doesn't do anything because you are at the leftmost point. So trying to move left doesn't do anything. So now you see how we are able to do some simple thing like this, like shifting everything to one step to the right, and writing a hash at the beginning. This was accomplished using a Turing machine. So like this, so this is a fairly simple task, but if you see the kind of things that we talked about here, right, move everything from left to right, crossing off, all this can be accomplished because these are fairly simple tasks and these can all be accomplished using states, right. So the point here is that we will not be going through things in this level of machine level detail or the state level, rule level detail. The point is that from now on we will just take it for granted that these kind of simple things can be done and we will not bother with the details. If you want, we can get out the details, but we will not be doing so just for the sake of time. We will want to see other things that we can learn about Turing machines. Okay, so we will resort to high level language. When I say high level language, I mean language like this. So depending on how high, this is not that high actually, this is still quite amount of detail, but it is not at the level of details of states and transitions. That's what I mean by little bit high level, so some maybe medium level detail. Okay, so this we saw, and the next thing I want to say is we can use Turing machines to compute functions, right. So suppose we want to increment a function, right, increment a number, sorry. Suppose the Turing machine, there is a binary number w1, w2 up to wn, right, and let's say we want to increment this number. Let's see how to do this, and just for the sake of simplicity, let's assume that the tape contains a hash symbol, okay, at the leftmost endpoint. Why this assumption helps is because this hash symbol helps us to indicate left end. So this tells us that we have reached the left end point. Otherwise, there is no way that Turing machine can know that it is at the left end point. So let's see how to increment something. So maybe we'll try to write some number. Let's say hash 00101. Okay, blank. Let's see what happens. So first we move to the rightmost end. So basically we look for blank and we get to the rightmost end. Okay, so we come to the rightmost end, and then okay, so we come to the blank and then we can come back one step, right, once we see the blank. If the current symbol is 0, we make it a 1 and that's it. But here the current symbol is not 0, it is a 1. So then so basically the point is this: if the number was something like 1000, the incrementing is 1001, right? So once we make the 0 to 1, we are done. But if we want to increment 1001, we actually have to change this to 0 and do something to the bit to the left side of it, because there is a carry operation happening. So that is why if the current symbol is 0, we move to the left end and accept, right? This is done. But if the current symbol is 1, it is kind of, you just move one step to the left and do not accept, you continue. So maybe I should write here, the goal is to increment 1, to increment W, right? So this is the increment means adding 1 to it. So now the current symbol is 1, right? So the 00101, the current symbol is 1, so you make it a 0. You make it a 0 and then you move one step to the left, right? And now the current symbol is 0, so now you just make it a 1, right? And since the current symbol was 0 was made into a 1, we can follow this rule, the first rule. We just move to the left end and you accept. So you come here and you accept, and the hash symbol will tell us that we have reached the left end, right? So we can come back to the left one step until we stop when we reach a hash. That's why the hash is helpful. So that is, these two rules will take care of almost everything. Just that in some cases we need to do something more. So let's see why. Suppose the number was 111. So basically a string of all ones, right? So now when we increment this, the resulting number is going to be 1000. So basically we need to get to hash 1000, meaning we need to go push everything one step to the right. From a 3-bit number I am going to a 4-bit number, right? So that requires some work. So let us see how this is done. So we first come to the leftmost point, right, this one, and this is first made into a 0, okay, and then you come to the one step to the left, further left, and you have a 1. So this is made into a 0, right? So you change it into a 0, and you come here, and this also you make it to a 0, and then you come to the left, but now we see a hash symbol. So if we see a hash symbol, this part kicks in, right? So if the current symbol is hash, what we do is you change it to 1, right? So you change this hash to 1. So now this is the tape. You have 1000, and we are kind of done. We have incremented the thing, but we started with this hash at the left side. So the output that we desire is hash followed by the incremented value, right? So how do we do that? We have to move everything by right to 1 bit and put a hash insert a hash here and shift everything by one side, right? So that is exactly what we described above, right? You shift everything to the right and add a hash at the beginning, and we can do that, and then you accept and stop. So this is how you would implement a increment function, okay? So again, things are not in full detail here, but the point is that we can implement it in full detail if we want. Finally, one more example. So this is kind of like testing multiplication, okay? So this is like trying to see how to do multiplication, right? So the language here is C. Language is called C. It's a power I, b power j, c power k, where k is the product of I and j. So k is I multiplied by j. So let's see how to do this, right? So you have, let's say we have A, B, B, C, 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 okay? So you first check whether the input is of the A star, B star, C star. In fact, I am saying that I, J, K are all at least 1, so A plus, B plus, C plus, right? So check whether the input is of this format. In fact, this is something simple. Even at DF, this is actually a regular expression, right? This is something that a DFA can itself handle, right? So you want A star, B star, C star, but at least 1A, 1B, 1C, A plus, B plus, C plus, right? So this is something a DFA can check. and then you come back to the left side. So this is something simple, I won't spend much time. And the coming back to the left, we may have to have a hash symbol, right? So this is something like the dollar that we used to put at the bottom of the stack. Like that, we put a hash symbol to the left of the input, because you keep coming left, and finally you reach the hash, and then you know that you have reached the leftmost. Otherwise, there is no way to tell, right? Okay, so now we do that. Let me just get that out of the way. Maybe I'll put the hash, right? So now what we do is we do the following. We cross the A, you cross an A, you cross one A, and then you go and check, you go till you see the B's, right? So first you see a B, you cross one B and then you cross one C. Then you come back, you cross another B, you cross another C. Then you come back, then you see that there are no B's. So all the B's are crossed out, right? So now you decide to erase this. So now, so basically you want to check that number of A's multiplied by number of B's is equal to number of C's. So here number of A's is 3, number of B's is 2, and number of C's is 6. In this case, it is a instance that should be accepted, right? So for each A, you cross out B's and cross out C's, and after which you uncross the B's. You uncross the B's, and now you strike out the next A, right? And then you cross out a B, you cross out a C, you cross out a B, you cross out a C. Now you again remove the crossing of the B's, you strike the A, you cross out a B, you cross out a C, you cross out a B, you cross out a C, and now you see that all the A's are crossed out, and now you check whether any C's are remaining. If any C's are remaining, you reject. If no C's are remaining, you accept. So in this case, everything is crossed out, so you accept. So suppose, let's say there was one more C, right? In this case, you would have rejected, right? So here the number of C's is more than the number of A multiplied by the number of B. So on the other hand, we could have had some situation like this: A, B, C, something like this. So here you would run out of C's first. So in this case, you would have struck out an A, then this B, this C, this C, and then you would unstrike the B's. You strike out the A, this B, this C, this C, and then you again unstrike the B, strike out the A, this B you strike out, but then there are no C's here. So if there are no C's here, again you will reject. If at any point you strike out a B but you do not have the C's, you reject. That is what is happening. That is what is happening here. If at some point you struck out a B but there are no C's to strike out, you reject. Otherwise, if all B's, everything is fine, but at the end you see everything is matching up, then you accept. So this is how you can use Turing machine to kind of do multiplication or kind of verify multiplication, right? So here that's what you are doing, right? You are checking whether number of C's is equal to number of A's multiplied by the number of number of B's, right? So this is these are some examples of Turing machines, right? So just to quickly summarize, we said what are the three possibilities for a Turing machine on a string. One is to accept, one is to reject, and one is to loop. If a Turing machine, so what is it, and two main definitions, two important definitions, I will repeat. A language is Turing recognizable or recursively enumerable if some Turing machine recognizes it, meaning it accepts all the string in the language and does not accept any string that is not in the language. Does not accept can mean two things: reject or loop. We say a language is decidable, or a Turing machine decides that language if it accepts every string in the language and rejects every string not in the language, meaning it does not loop on any string at all. All the strings in the language are accepted, all the strings not in the language are rejected. So we say language is decidable if, or recursive, decidable or recursive if there is some Turing machine that decides it. And then we saw some examples like how to check how a Turing machine could do some simple things like check some simple languages like a being 0 to the 2 power n, or do simple tasks in which we went into some detail, and some computing function like incrementing a string, incrementing a bit, a binary number, and checking some simple languages, right. So that completes this lecture, which is lecture number 28. In the next lecture, we will see variants of different types of Turing machines. So what we saw is deterministic Turing machine with a single tape. We will see different types of other types of Turing machines. Thank you.